sketch a plot of these functions. Okay, so this is going to be long. There are 18 functions. So let's start. Okay, with the first one. This is f is e to the x sine of x, right? So now everything that multiplies the sign. So we have the sign, right? You know, the sign does something like this, oscillates between -1 and 1, right? So what the exponential does is that for every value of the sign, you get it amplified by the exponential. So what you have is that if the sign is positive, it will have a value as high as the exponential, and if it's negative, it will have a negative value. Okay, and so if you have this, if you plot this exponential and the negative exponential, right, minus e to the x and e to the x, then the sign will be 0 at 0, or it's points of 0, right? And then here it will be 1, but it's not 1, it's 1 times the x e to the pi over 2, right? So it will be something like this, and then it will oscillate, and at this point it will touch here, and it will touch here, and it will touch down here, and you see how this goes, right? And also the same for the negative, right? It's just right. So this is how it looks like. Okay, so this is e to the x sine of x. Okay? You don't need to really compute anything about it. You just need to think about what this function means, right? Now let's do the second one. F is the square root of x squared minus 1 minus 1. Now what's the domain of this function? Well, the domain of this function is this has to be greater than 0, greater or equal than 0. Okay, so the x squared minus 1 is this parabola, right? And has roots at -1 and 1. So the domain is minus infinity 1, minus 1, sorry, 1 infinity. Okay, now at these values, it has at f at -1, this is 0, so this is -1, and f at 1 is also minus 1, right? So it's like the two values where the domain stops. Sorry about this. The domain stops, and then you have, let's see, this is -1, right? So this the point here, this is x minus 1, 1, minus 1, right? And now obviously this is an increasing function, so this is going to be like this and like this, but you can compute the roots of this. So this is f of x is equal to 0 when the square root of x squared minus 1 is equal to 1, or in other words, when x squared minus 1 is equal to 1, or in other words, when x squared is 2. So either minus the square root of 2 or plus the square root of 2. So it's easy to see that the function is going to be like this. Well, if I crossing this point, it's like this, right? This is also an even function. You can see the limit when f goes to infinity is infinity. You can compute the, if you want the derivative, to realize that this is decreasing when x is negative and increasing when x is positive. So something like this is 2x divided by the square root of x squared minus 1, right? So this is positive when x is positive, negative when x is negative, and so on and so forth. Okay, and also you can compute the second derivative to see that this function is concave everywhere, right? And let me show you the actual plot of the function using the nodes. So you have every function in this exercise already plotted in the lecture notes, okay, in the last pages. So that's what this looks like when it's plotted by a program. Okay. Okay. Let's do part 3. Okay. 3 is f x to the times e to the 1 over x. Okay. Now we know that e to the 1 over x is a discontinuous function that has an asymptote at 0, right? So when the limit when you go to 0 from the right of this is going to be plus infinity. The limit when you go from the left is 0. Let's see what happens with f here. So the limit when x goes to 0 on the right of f is, and we can change the variable, right? Say t is 1 over x. This is equal to the limit when t goes to plus infinity of 1 over t times e to the t. And you can compute this using L'Hopital or whatever. This is infinity divided by infinity, but this infinity is much greater in a sense. This goes to infinity much faster than this. So the limit on the right is going to be plus infinity. The limit when x goes to 0 on the left of this is going to be 0, because this is 0 and this is also 0. Okay, so we have this interesting. This is going to be like this. An asymptote on the right, and then on the left the limit is going to be like this. Okay, and you can see from here that f is negative when x is negative, because the exponential is always positive, so the function is going to be like this. It's going to be increasing, right? Now we can compute the derivative of this, and this is going to be e to the 1 over x plus x e to the 1 over x times minus 1 over x squared, or in other words e to the 1 over x times 1 minus 1 over x. Now this is 0 only, this is always positive, this is 0 only at 1. So we have a maximum or minimum or extrema at 1. So it has here, we don't know, it seems like it's going to be a minimum, right? But in order to check that, let's see what happens when the limit when x goes to plus infinity of f. Now when x goes to plus infinity of f, this goes to 1, right? E to the 1 over x when x goes to infinity is 1. So actually when x is very large, let's say, then f is approximately equivalent to x. So this limit is plus infinity, and the limit when x goes to minus infinity of f is also minus infinity. So we have so this is going to be like this and like going to this, but we have an inclined asymptote. So in order to compute the intercept of that asymptote, what we have to do is compute the limit when x goes to infinity of f minus x, which is the asymptote. So here what we have is the limit of when x goes to plus infinity of x times e to the 1 over x minus 1. Okay, now and now this is going to 0. Wait a minute. What did I did? Yeah, so this is an intermediation, sorry. So this is yes, the limit when x goes to plus infinity of e to the 1 over x minus 1 divided by 1 over x. And you can actually see that this is the same as the limit when t goes to 0 of e to the t minus 1 divided by t. And we know that this is equal to 1. So the inclined asymptote is x plus 1. So if we have, this is 1, let's see if we can plot it like this. This is x plus 1. And so the point here is going to be a minimum at minus 1, sorry, at 1. So the function is going to be like that. And it's also going to be like that. Okay? That's how you compute this. So this is actually the value of x times e to the 1 over x. Let me see the plot. And this is what we got. Okay? Okay, so let's do part 3. Sorry, part 4. Okay, part 4. We have f is x squared times e to the x. Now, let's say, well, this obviously has a zeros at 0, right? It's only 0 at 0 because e to the x is always positive. And this is, so this function is going to be, actually, this is going to be always positive except at 0, which is 0, right? So let me write it here. At 0 we have this. And then let's see, the derivative is going to be x squared e to the x plus 2x e to the x. So x squared plus 2x e to the x. So in other words, x plus 2 e to the x. So we have two different points where the derivative is 0 at 0 and minus 2. Let's compute the second derivative to see what happens with these two guys. So we have again x squared plus 2x e to the x, and then plus 2 e to the x plus 2x to the x. So in other backwards, this is x squared plus 4x plus 2 e to the x. So when is this going to be 0? We have x minus 2 plus minus, minus 4. 16 minus 8 divided by 2. This is minus 2 plus minus, and then we have this is 8, 2 times the square root of 2 divided by 2, the square root of 2. Because see, these are the points where this derivative, second derivative changes sign, and it's going to be, let's say, this is a positive parabola. So when x is smaller than the smallest root here, so when x is very negative, this is going to be positive. If x is smaller than minus 2 minus the square root of 2, then it's negative if x is between these two things, minus 2 plus the square root of 2, and the second derivative is positive if x is greater than minus 2 plus the square root of 2. Okay, these are all positive, negative numbers where the concavity or the convexity changes sign. So let's see. Okay, so what's important for us is that this value here at 0 here, it's going to be a minimum, right? Because the function is concave there, so it's going to be something like this. And then at minus 2, let's say here, we have that, let's say, this is minus 2 here, right? So the function is, the second derivative is negative, so we have a maximum here. So, and then we can compute the limit, let's see, the limit when x goes to minus infinity of f, this goes to 0, right? So this is 0, so we can see that this is going to be like this. Boom. Chains of concavity, now chains of concavity again, you go like this. Okay, and then up to here, obviously the limit when f goes to infinity is infinity, so you have something like this. Okay, that's our function. Okay, let me show you the value. It looks, has some resemblance, right, to it, more or less. Okay, let's do the next one. Let's do part 5. 5 is f is equal to x minus 2 times x to the 2 over 3. Now obviously there are two zeros here, at 0 and at 2. Okay, now let's see, the derivative of this, if you do it, is 5x minus 4 divided by 3 times the cubic root of x. Now this is 0 at 4/5, okay, which is slightly smaller than 1. And let's say, so we can say that yeah, this is going to be positive when x is greater than this, and negative when x is smaller than this. So the function, this is positive, negative, so this is a minimum, right? Minimum. You can check the sign of the derivative, and that's it in this case. So let's see, let's see some plots. We have 0 here, we have a 0 here, and a minimum between these two. So if you have to go from this to this, and there's only a minimum, it stands to reason that the minimum has to be negative, right? And it does, right? Because x to the 2/3, this is positive if at 4/3, with x minus 2, this is negative. Okay, so this is something like that. And this seems to be increasing, right? The limit when this goes to infinity is plus infinity. Okay, something like this. And then what happens at 0? Okay, at 0, this is going to be non-differentiable, right? So we have a cusp. Okay, so what happens? Something like this, right? Let's see the function at 0. When the limit when you go to 0 on the left, this is going to be negative, right? And this is going to be positive because it's x squared. So yeah, so this part is negative, right? Now what happens to this? in order to get this, we need to compute the second derivative because we want to get the concavity of this, right? The second derivative, if you compute this, is 10x plus 4 divided by 9 cubic root of x squared, right? So this is 0 at minus 4/10 or minus 2/5. Okay, so now when x is greater than minus 2/5 and smaller than 0, so greater than this, sorry, this is going to be positive, so this is going to be concave up until this point. This is minus 2 over 5, and then you have an inflection point here. Okay. An inflection point at this point. Okay, that's what this looks like. And let me show you the plot. Okay, you see, you have this, and then you can't nearly see it because it's really close here, but it's half here, and then it changes in the concavity of the function. Okay. Okay, let's keep doing this. Part 6 is f is x squared minus 1 times the logarithm of 1 plus x divided by 1 minus x. Okay, so first of all, let's see what's the domain of this function. Well, the domain of this is, you can actually write it like this: the logarithm of 1 plus x minus the logarithm of 1 minus x. So we want x plus 1 to be greater than 0, and we want 1 minus x to be greater than 0. This implies that x has to be greater than minus 1. This implies that x has to be smaller than 1. So the domain of f is minus 1, 1, actually. Okay? What happens at the edges of the domain, right? So what happens when the limit, when x goes to minus 1 on the right of f, right? So then we have the limit when we go to the right of 1 minus 1 of this. So we have two limits, right? The limit of this times the logarithm of 1 plus x, and then plus the limit of this times the logarithm of 1 minus x. But this is going to be 1 minus minus 1, the logarithm of 2, and the limit of this is going to be 0. So the interesting limit is this one. Okay. Now in this case, this goes to 0, but this goes to minus infinity, right? So we need to, this is an indetermination, 0 times infinity, right? We need to solve this. One way to do it is using L'Hopital, for instance. So we have the logarithm of 1 plus x divided by 1 over 1x squared minus 1. Okay, and now this is infinity, infinity. And we can use L'Hopital's rule. We can differentiate both the denominator and the numerator. You have 1 over 1 plus x, and then this is minus 2x divided by x squared minus 1 squared, right? But now, yeah, is this correct? If I'm correct, wait a minute. Yes, right, because yes, okay. So now, let's see. We have this thing goes multiplying here, so we have the limit when x goes to minus 1 positive. But this is, you can see this is x squared minus 1, this is x plus 1 squared times x minus 1 squared. So this and one of these go away, and so you have the limit of x plus 1 times x minus 1 squared divided by minus 2x. And this thing don't matter, but this thing goes to 0, so this limit is 0. Okay, so let's see. We compute this is minus 1 and this is 1. At minus 1, the function is 0, or the limit would be 0, but it's not really 0. Okay, so that's an avoidable discontinuity. What happens at 1? Well, we have the same thing, right? On the left, right? We have the same thing, but instead of having this limit important, because this is going to be the logarithm of 2 again, the important one is the logarithm of, this is minus the logarithm of 1 minus x, okay? This is the limit, and if you do the same thing, you will get the same result again. You realize this is going to be exactly the same limit as before, so you have here, the limit would be 0. So two avoidable discontinuity is at minus 1 at 1. Okay. Now, when is this function 0, right? This is 0 at minus 1 and 1, but this doesn't matter. When is this 0? When the logarithm of 1 plus x is equal to the logarithm of 1 minus x, or in other words, okay, you want this is equal to 1, but this is only equal to 1 when x is equal to 0. Okay, so there's a 0 here, right? And then let's see what else. We have the derivative of this function is going to be first 2x, right? The logarithm of this, and then we have the derivative of this thing, right? So we have plus x squared minus 1 times 1 over 1 plus x plus 1 over 1 minus x, right? Because the derivative of this is minus 1 over 1 minus x plus this. But you can see that this thing here is 1 minus x plus 1 plus x divided by 1 plus x times 1 minus x, which is 1 minus x squared, which is negative this. And so you have 2, this is, all of this is equal to minus 2. Okay, so let me write it here. This is equal to minus 2. And when is this equal to 0? Let's see. So when x is 0, right, at 0, this is negative 2, right? All of this is equal to 0. So we have this thing, right? And then so if this is like this, so it has to go like this, and this has to go like this. So this has to be, there has to be a maximum here at some point and a minimum here, right? This is how this works. You can try to compute the maximum, right? So when is x times the logarithm of 1 plus x divided by 1 minus x minus 1 equal to 0? And yeah, so you can try to approximate the logarithm when, you know, close to 0 and something like that. So you get that this is close to 1, the x is approximately close to 1 plus minus 1 over the square root of 2. You try to approximate again the logarithm with Taylor expansions. This you can see here that the function is odd, okay, and this is something that we hadn't said. You can see here that if you change the sign here and change the sign here, this is going to be minus this original logarithm. So the function is odd, which could have helped, but anyways. And so this is the plot of the function, right? As you can see, this is close to 1 over the square root of 2, which is 0.7. Okay. Okay, let's do part, what's now? Part 7. Okay. Part 7 is f equal to x logarithm of x. So the domain is positive values of x, sorry, but also without 1. So this is 0, 1, union 1, infinity. So you're going to have this is 0, right? We only consider positive numbers. What's the limit when x goes to 0 on the right of x divided by the logarithm of x? This goes to 0, and this goes to minus infinity. So actually this goes to very large numbers, this goes to very small, so it's obviously that this is going to be 0. Okay, so this is 0. Now when x is positive but small, this is negative and this is positive, so this is going to be negative. So this is going to be something like this, I don't know, the concavity, right? And then we have an asymptote here at 1. Okay. Now what happens, the limit when x goes to 1 on the left of x divided by the logarithm of x, this is going to go to 0. This is going to be it's going to go to 0, but from the negative side. So this is going to be negative infinity, right? And then from the positive side you have 1, and then this is going to go to 0, but from the positive side, so this is plus infinity. So you have something like this and something like this. Okay, and then let's see. So it seems like this is going to be like this, maybe, but maybe there's like a chance of concavity. We need to check that. The limit when x goes to infinity is obviously infinity, because x, so the logarithm of x is negligible when x is very large. And let's see, so let's get the derivative, right? F prime is going to be the derivative of x times the logarithm of x, all of this divided by the logarithm of x squared, minus, and then x divided by x, so this is 1. So this is only 0 at 1, right? Sorry, not at 1, at e, right? When x is e, this is 0. So e is somewhere around here. You can see from this is the only extreme of the function. This is differentiable in this part, so this is going to be a minimum, right? You don't need to really check that much, like this. But maybe, okay, so maybe this is not a good way to plot, because we don't know the concavity of the function. So let me check the concavity. So we have the second derivative. If you compute this, you will get 2 minus the logarithm of x divided by x times the logarithm of x cube. And so this has let's say this is have different behaviors. Okay, when this is between 0 and 1, okay, let me say 0, 1, and e. So what the logarithm of x is 2, that means that this is 0 at e squared, right? So this is 0, 1, e squared, right? So okay, between 0 and 1, this is positive, but this is negative. So the second derivative is negative. Between 1 and e squared, this is again positive, this is positive, and this is positive, so this is positive. And now after e squared, this is negative, this is positive, so this is negative. So we have the function is concave between 0 and 1, okay, so we have here, okay, is convex. Let me erase this part. It's convex up until e squared, so this is e, and let me see, this is e squared, for instance, okay, and then there's concave again, okay, so this is going to plus infinity like that. So actually this is the function, and this is what this looks like. Yeah, the change in concavity doesn't look like much, but it's there, right? And so we have this thing like that. Okay, let's do part 8. Let's do part 8. F of x is x squared minus 1, x squared plus 1. Now that's an interesting one. Okay, x squared plus 1 is never 0, right? So the domain of this function is the reals. We have, this is 0 at 1 at minus 1, so f at 1 is, f at minus 1 is equal to 0, right? So, and then, yeah, so let's see, this is going to be like that, this is 1 and minus 1. This is always positive, so this is like a parabola, and the minimum value of this function, you can see it's going to be at 0, okay? At 0 it's going to be minus 1, okay, something like this. But you can check with the derivative. The derivative is going to be, let's see, 2x times x squared plus 1 minus 2x times x squared minus 1 divided by x squared plus 1 squared. And then you have, let's see, is correct? This 2x x squared and 2x x squared go away, so you have 4x divided by x squared plus 1 squared. And now obviously the only only 0 of this is 0, okay, so then we have this. And this is a minimum because you have this is negative for negative x and positive for positive x, so you have a minimum here. If you compute the second derivative, you will see that this is 4 minus 12x squared divided by x squared plus 1 cube. So the signs of the second derivative, you have the roots of this are x squared equals to 4 divided by 12, so another 1/3. So this is minus 1 divided by the square root of 3, 1 divided by the square root of 3. And this is a negative parabola, right? So it's going to be positive in between these two and negative in between these two. So you have 1 over the square root of 3 is actually smaller than 1. So this is, let's say, how to plot this. This does something like this, and then change the concavity, and also here as well. And also this looks like something, and also, but what you can see here is that the limit when x goes to infinity of f is 1. We have an horizontal asymptote. Okay, so this is what this looks like. Okay, and let me see. Okay, this is what you have. Okay, so the change of concavity here and then the asymptote. Okay, let's do part 8. Sorry, 9. Part 9 is f e to the 1 over x again divided by 1 minus x. Now again we have an asymptote at 1, right? Asymptote, vertical asymptote at x equals 1, and at 0, right? We know that at 0 this is going to be, let me write this, this is like at 0, x equals 0, x equals 1. We know that this is going to be plus infinity like this, right? This is 1 minus 0, so this is going to be plus infinity, and on this is going to be 0. And then in this case we have the limit when x goes to 1 on the left of f. This is going to be positive, and this is going to be positive, so this is going to be plus infinity. And the limit when you go to x on the right, sorry, on 1 on the right, is minus infinity. So you have something like this, something like this. Now, this is always positive, so there's no zeros of f. So in this case, you will have a maximum here. We don't know where, but we can compute it later. And this is going to go, let's see, the limit when x goes to infinity of this is 0, and 0 divided by infinity, so this is infinity. So this is going to be like this. Okay, and from here we have maybe this has to go to infinity. This is always positive again. This is positive, so maybe there's a maximum here. So let's check the derivative. Okay, the derivative is e to the 1 over x times x squared plus x minus 1 divided by x squared times 1 minus x squared. Okay, you do it, you will see. Now let's see. This is going to be 0 when this is 0, and the two zeros are at minus 1 minus the square root of 5 divided by 2, and minus 1 plus the square root of 5 divided by 2. Now this is the minimum here that I was telling you about. Okay, and the other one is a negative number, which is going to be like this, for instance. So that's a maximum, right? We don't need to check really. And so yeah, it's obvious that we will have a change of curvature here at some point, and here, right? We maybe want to check this, and here it seems that the function is going to be convex and this is going to be concave, but you want to check that using the second derivative. Okay, but yeah, I'm not going to do it. You can do it on your own. Okay, okay, let me check the function. This is what it is. This thing, it changes this here, and here it's so big. When x is so small, then x to the a to 1 over x is so big that you don't see it, right? This function is maximum here. So okay, let's do part 10. part 10 is f is the logarithm of the, so what is the product of x minus 1 times x minus 2. So let's see, we want this to be greater than 0, so this is a parabola, it's x squared minus 3x plus 2. Okay, so the domain here is going to be, so this is a positive parabola, the roots are 1 and 2, so this is going to be positive between minus infinity and 1, and between 2 and infinity. Okay. Now the zeros of this function are when x minus 1 times x minus 2 is equal to 1. You compute this, this is parabola, so this is just compute the root of this parabola, right? And the roots of this are x1 is 3/2 plus the square root of 5 over 2, and 3/2 minus the square root of 5 over 2. Now square root of 5 is smaller than 0, sorry, than 1, sorry, it's smaller than 3. So this is going to be smaller than 3, and this is going to be smaller, so greater than 0. Okay, so let's see, if we plot these two things, we have the asymptote at 1, the asymptote at 2, somehow. This is forbidden territory, right? This is going to be minus infinity here and minus infinity here, because that's what the logarithm does. And then we have these two zeros. One it's positive but close to 0, something like this, and one is positive but close to here. Let's see if I can. So this is going to, it seems like it's going to be like this. And one way to see it is that this is actually, you can write the logarithm of x minus 1 plus the logarithm of x minus 2, right? And so let's see, when let's see, so when x so when x is positive, this is the sum of two logarithms, so you have this. And when x is negative, well, here it doesn't work like this because it's not, this doesn't work when x is negative, right? But you can see that this is going to be like kind of symmetrical with respect to 1 and 2. Okay, and actually you can prove that the function is symmetrical with respect to this axis 3/2, okay, which is what we have here. Okay, let me show you the logarithm, right? It's the same, symmetrical around this x-axis. Okay. Okay, so let's see. Let's do part 11. 11 is f is e to the x divided by x times x minus 1. So we have two asymptotes at 0 and at 1. Let's see. We have x equals 0, x equals 1. And let's see, so when you go to 0 from the left, this is always positive, this is negative, and this is negative, right? So you have positive asymptote. When you go to 0 from the right, this is positive, but this is negative, so this is like this. Let's see, you go to 1 from the right, this is positive, but this is negative, so again negative, and this is positive, something like this. Okay, now the limit when x goes to infinity of f is going to be plus infinity, because this goes to infinity but much faster than this, and the limit when x goes to minus infinity is going to be 0, right? So we have a horizontal asymptote here. And so now let's see, let's just connect the dots. This is never going to be, this is never going to cross the x-axis actually, because the exponential is never 0, so this is going to be positive. Okay, so unless something weird happens, this is going to be like this is going to be like this, and this is going to be like this. No zeros, right? Now let's check, we need to find these two optima, right? So f prime is going to be e to the x, and then x squared minus 3x plus 1, this is what you get. divided by x squared times x minus 1 squared. And so f prime is 0 when this is 0, and the roots of this are x1 3/2 plus the square root of 5 over 2, and then x2 is 3/2 minus the square root of 5 over 2, so exactly the same as in the previous exercise, right? So between 0 and 1 and between 2 and 3, and you have it here, okay? So this is what you get. Okay. You can actually check that there is no change in concavity here. You can compute the second derivative and see that the function is convex here, concave here, okay? Okay. Let's keep doing this. Part 12 is here. F is 2 times the sine of x plus the cosine of 2x. And so let's see. This is an interesting one, right? So we have the sine of x, so we know how the sine is. We have this, right? So 2 times the sine means that this goes to 2 and minus 2, and then you have the cosine of 2x, which is, it starts here, and it does double period, right? So this is in 2 pi, right? In 2 pi, in 1 pi it already does the same thing, so it does, let's say, pi halves, it goes to minus 1, right? Yes, pi halves, it goes to minus 1, and then in pi it goes to 0, sorry, yes, cosine of pi, sorry, 2 pi, so this is, let's say this is pi, I'm plotting this terribly, and then this is, you do it again, let me see, so this is in pi, this is pi halves, and then you have again the same thing. So 2 periods in 2 pi instead of 1, right? So now if we combine these two things, what we need to check is what's going to happen in the different maximums and minimums, right? So let's compute some values, right? So we have if x, we have this 2 times the sine of x and the cosine of 2x, right? And so we have x pi over 4 pi halves 3 pi over 4 pi 5 pi over 4 6 pi over 4 3 pi over 2 7 pi over 4 and then 2 pi, right? We have this and this. Let's start with cosine, maybe it's easy. So this is going to be at 0, this is going to be 1. At pi over 4, this is going to be pi pi halves, right? So this is 0. And at pi halves, this is going to be pi minus 1. So this is going to be like that. 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1. Okay, so it starts again. The sign is going to be 0. At pi fourths, it's going to be the square root of 2 over 2 times 2, the square root of 2. At pi over 2 is 2. Then we have, again, the square root of 2. We have 0. We have minus the square root of 2, minus 2, minus the square root of 2, 0. Okay, now if you compute f, which is the sum of both times, you have 1, the square root of 2, 1, the square root of 2, 1, minus the square root of 2, minus 3, and then minus the square root of 2, 1. Okay, so let's see how we can plot. This is just one period of the function, right? From this is 2 pi, we have pi halves, quarters, and that's it, right? So what we're saying is that at 0, f is 1, so this is 1, square root of 2, 2, okay? 2, and then this is minus 1, minus 2, minus the square root of 2, minus 3, okay? Okay, now at 0, this is 1. Then at pi fourths, this is square root of 2. It goes to 2, no, sorry, 1 here again, square root of 2. and then 1 again at pi, and then we go to minus the square root of 2 here at pi 5/4, minus 3, so we have a 3 here, minus the square root of 2, and 1. Okay, so if you want to connect the dots here, you can try to compute this, using the derivatives and the second derivatives, but you can see here what we have is an oscillatory function. It does something like this. Okay, so that's an interesting one. So that repeats itself every period of 2 pi, right? Let's see the plot here, right? So that's what we get. So that's an interesting way, and maybe later in your degree you will see that we can always write any periodic function such as this as a combination of sines and cosines, right? It's what's called a Fourier transform of any function. Okay. In this case, it's already written like that. Okay. Now let's see. So we have where were we? Part 13. 13 is f is x minus 2 divided by the square root of 4x squared plus 1. Now, let's see. Well, obviously there's a 0 at 0, right? And the function is going to be negative for x smaller than 2 and positive for that, right? And let's see you can see that this is approximately equivalent to 2x when x is very large, so you can see that the limit when x goes to plus infinity of f is going to be x divided by 2x is 1/2, and the limit when x goes to minus infinity of f, again this is positive 2x and this is minus x, so this is going to be minus 1/2. Again, we've seen limits like this before, right? So you need to be careful with the signs. So the function is going to be this is a 2, right? This is 1/2, this is minus 1/2. Okay, so the function is going to be like this, and maybe is it going to go below or not? We need to check if there's a maximum or minimum or something. So the derivative of this function, if you compute it, is 8x plus 1 divided by 4x squared plus 1 2 to 3 halves. So that there's obviously a minimum, sorry, a 0 of the derivative at minus 1/8, so it's around here, right? And it seems, so the function, so that, sorry, this is going to be, let's see, increasing, right? Yeah, this is a minimum, right? It's decreasing when x is negative, and decreasing, so this is going to be like this. Let's see. Yeah, so if it's decreasing for this, it has to go from here, right? It has a minimum here, let's see. And then it crosses the x-axis here. This is y equals 0. It crosses the x-axis, and then it does like this, something like this, okay? So obviously there is some change of concavity here, but this is roughly how the plot would look like. Okay, let's see if we can see it. Okay, exactly this. Okay, so you have the two asymptotes, and here it. Okay. Okay, let's do part 14. We're almost there. We have f is the square root of x, the absolute value of x minus 4. So obviously the domain of this function is the reals, right? Because this is always let's see, not negative. But so if x is 4, so this is like centered at 4, right? So if x is equal to 4, this is just like this, a square root in this side, right? And if you do f is smaller than 4, but yeah, so you can see that this, because of the absolute value of x, right? The absolute value of x minus 4 is like this, right? With this centered at 4, right? So this is the same, but taking the square root of both branches, so you have like that, right? This is what is going to happen. Okay, so this is actually the this function. Okay, and then let's see, part 15 is f equals 1 over 1 plus e to the x. This is never going to be 0, always positive. Now we're interested in the limits when x goes to infinity, right? The limits when x goes to plus infinity is 0. The limit when x goes to minus infinity is 1. So you have two asymptotes, y equal 1, y equals 0. Now at 0 this is going to be 1 half, okay, so it's like this. It goes to here from here, so maybe it does look like this. Okay, something like this. You can try and compute the changes in concavity maybe, and things like that, but this is enough to actually plot the function, and this is what you get here, okay? Exactly this. Okay, let's do 16. F is e to the 2x divided by e to the x minus 1. Now, let's see. Let's compute this is going to be 0 never. It has an asymptote at 0, right? When you go to 0 from the right, this is positive. This is positive, so you have it here, and this is negative, right? Like this. Now, when the limit when f goes to, so when x goes to plus infinity of x is going to be infinity, right? Because you can divide everything by e to the x, and you still have it as something that goes to plus infinity. And the limit when you go to minus infinity is actually going to be 0, right? So you have 0 divided by minus 1, which is 0. Because this is negative, it could go cross the x-axis, but I just said it doesn't cross the x-axis, so it just like goes like this. And then this is going to go to plus infinity, so this has to have a minimum here. Okay, let's compute the minimum. The derivative is e to the x, sorry, e to the 2x times e to the x minus 2 divided by e to the x minus 1 squared. And this is going to be 0 whenever e to the x is equal to 2, or in other words, that x at log of 2. Okay, this is log of 2. That's the minimum. You can want to compute the second derivative to show that this is going to be convex and this is going to be concave, but that's pretty much it. Okay, see. Okay, and then two more. We have f of x is e to the minus x sine of x. This is exactly the same as the first one we saw, right? But instead of having e to the x, we have e to the minus x here. This is e to the minus x, this is minus e to the minus x. And so the sign goes like this, and like this, okay? So yeah, you can try and study it in more detail, but it's exactly the same as the only one. Okay, it's not like mirroring against the x-axis, the y-axis, sorry, because the sign is not mirrored, but it's almost like that. Okay. So that's 17. That was easy. Let's do 18. This is x squared times the sine of 1 over x. Now we know that this function has a limit equal to 0 at 0. We know that there's this bound between, positive x squared and minus x squared, as we have done previously. But now that's interesting thing. So the sign will go like this, and this would go like this. But an interesting aspect of this one is that we know that the limit when x goes to plus infinity of the sine of 1 over x divided by 1 over x is 1, right? But this is equal to sine x times the sine of 1 over x. So this is equal to f divided by x. So that means that the limit of f divided by x when x goes is very large, this is 1. So that means that there's an implied asymptote. So we need to compute the limit when x goes to plus infinity of f minus x. And when you do that, you get, let's see, this is the limit when x goes to plus infinity or minus infinity, doesn't matter, of x times the sine of 1 over x minus 1, right? Now this limit is 0, right? Sorry, 1. So this is 1 minus 1, so this goes to 0, right? Or infinity divided by 0, but you can also see that you can get the limit when x goes to plus infinity of, let's see how to write this. This is the sine of 1 over x divided by 1 over x minus 1 divided by 1 over x. And you can change the variable here, t as usual equals 1 over x. So this is the time, let's say, the sine of t, the limits when t goes to 0 of the sine of t divided by t minus 1 divided by t. And you can compute a L'Hopital, use L'Hopital's rule to deal with this. You get that this is the cosine of t, times t minus, and then the sine of t divided by t squared. And well, maybe L'Hopital is not a good idea here, sorry. So let's use Taylor expansion. So this is the sine of t, this is 1, and then minus sine of t is x cubed, t cubed over 6 divided by t, this is t squared divided by 6 minus 1 divided by t, 1 minus 1, the limit of this is 0. Okay, so the asymptote, the asymptote is going to be x. Okay, so interestingly, this function is going to be like this, and then it goes like this, and something like this, if I plot this correctly. Okay, there's an inclined asymptote in this one, and you can see it here. Okay, that, and you get to large scale the last. So what you have is actually that the oscillations of the sine, you know, when you get to large x, it stops oscillating at all, and so it just goes to that. Okay, and so that's the end of the exercise.